Welcome to the first example for the digital preemphasis filter component. In this particular setup, we'll examine the application of the DPE filter in a simple IMDD transmission system. Let us go over the components involved in this simple setup. The main layout indicates that a total bitrate of 224 gigabits per second is utilized with a PAM4 modulation format. As such, we have here 2 bits per symbol. Consequently, the symbol rate, or the baud rate, is 112 gigabauds per second, typical number for Ethernet transmission with the particular overhead involved in FEC encoding and decoding. As such, this is 200 gigabit per second payload transmission link. We will be relying on direct error counting for determining the total bit error rate after transmission. We're using a BR test set, producing data that's fed into the PAM pulse generator, generating a 4-level signal that is fed into a Mach-Zehnder modulator. As you can see here, the digital preemphasis component is meant to be dormant or disabled for the first run. And the electrical drive into the Mach-Zehnder modulator has an amplifier and a laser driver, followed by a bandwidth limiting Gaussian filter. So this filter will essentially emulate the bandwidth limitations of the connections into the Mach-Zehnder modulator. And we will be disabling this for the first run to demonstrate the performance of the link without any bandwidth limitation. We have a CW laser, Mach-Zehnder modulator, and 100 meters of single mode fiber. This is typical for data center type of distance. We have a PIN photodiode and a low pass filter, followed by clock recovery and PAM decisions, symbol to bit mapping, and then we fed back into the bit array test set. If we run the simulation as it stands, without any bandwidth limitation, we'll see that the performance is adequate. In fact, there is no recorded errors, BR is 0, and the simulation is error-free. This is also apparent from observing the eye diagram. You can see here that there is clear eye openings for all of the 4-level signal. Now, in an effort to emulate bandwidth limitations of the transmitter end, we will essentially enable this bandwidth limiting filter. So this is a bandwidth limiting Gaussian filter with 50 gigahertz cutoff frequency. And you can see here that the filter order is 1. So at the end of the day, this is actually your uncompensated filter response in the context of the digital preemphasis. Let us run the simulation now with the inclusion of the bandwidth limiting Gaussian filter into the drive of the Mach-Zehnder modulator. And it can be seen here that we have errors showing up, and the log bit error rate is minus 3.3, which is just below the FEC threshold of 1 e to the minus 3. And the errors can also be seen manifested in the eye diagram. The eye diagram is fairly closed due to the severe limitation of the bandwidth due to this bandwidth limiting Gaussian filter. In an effort to essentially compensate for this bandwidth limitation, we can see the parameters is a Gaussian filter with a cutoff frequency of 50 gigahertz and a first order. As such, we import the same parameters into the digital preemphasis. So if we now look at digital preemphasis filter, we're looking at the uncompensated filter response. It will be Gaussian, matching our bandwidth limiting filter, 50 gigahertz with a order of 1. Our desired filter is intended to be wide enough that it accommodates the actual inherent bandwidth of the modulated signal. In this current configuration, we don't have any pulse shaping involved. As such, we don't have any roll-off factor, and we're using a rectangular type of modulated signals. So just to capture the first lobe of this NRZ signal, 80 gigahertz Gaussian filter will be sufficient bandwidth to really accommodate the actual inherent bandwidth of the signal. And we'll enable now the digital preemphasis filter, and we see what differences it make in the performance of our link. And it can be seen right away that you have error-free operation with no errors, and observing the eye diagram, you see now that the eye diagram is fairly open and the ISI has been significantly reduced. This is actually one of the key benefits of the digital preemphasis component involved. And if we look at the component view, we have a look at the 2D diagrams, we can see the uncompensated filter response, our desired filter response and the digital pre-emphasis filter response shown in blue. If we just zoom in on this section here, you start seeing that your digital pre-emphasis is indeed compensating a fair bit of the signal. The depth of the filter is fixed to -100 as evident in the main tab of the DPE filter. We can also examine the performance of this filter under a digital implementation by enabling the DPE Z-domain coefficients with a 12-bit resolution, and we can increase the number of coefficients to, let's say, 512. And you can certainly save the values of these FIR coefficients and load them into a digital filter, or you could also load them into a experimental setup or a DAC driver if you have an FIR implementation prior to it. And you can see here that also you have error-free operation with digital implementation, and your eye diagram is error-free. It's not as good as the analog implementation we did initially, as there is always some effects due to truncation, windowing, and the finite resolution of the taps in the FIR coefficient. And we can certainly observe these coefficients here in the 2D view of the diagram, and you can see now we have the initial parts of FIR coefficients. These FIR coefficients are run at a very high speed, which is the analog speed of the symbol rate. You can certainly set your FIR implementation bandwidth to something that is more realistic, that is conformatory to your DAC resolution. So assuming this is 112 gigabaud per second, then if we want 2 samples per symbol, we will have 224 essentially giga samples per symbol, and that would be sufficient for having 2 samples per symbol in our implementation. And if we run this model here, we'll start now seeing a more sort of reasonable and expected response, where the speed of the digital analog converter that will be implemented after the FIR filter coefficient and within the hardware limitations actually is consistent and reasonable. You can still see here we have error-free operation, and observing the eye diagram, it's fairly open. And if we look at the digital FIR implementation here, we can see we have now our FIR coefficients, and presumably we could have gotten away with lower number of taps, as you can see the tap values are fairly small outside 256 tap coefficients. Thank you very much for your attention.